Well, since it's concrete design, I'll see if I can get you all to crack up, a couple times. Oh, yes. It's already started. There you go. You don't have the timing. That's what it is. All right. Let's settle down. We actually do have some stuff to talk about today. So number one, homework is due today. If you haven't already turned that in, do so. I do apologize about that modular ratio issue on problem 3. The solutions manual just flat used the wrong modular ratio, so the stresses didn't match. There is sort of a quirk, if you will, to the moments on problem 3. I mean, I'm obviously going to be pretty gentle when I grade it, but when we go through and do the solution and I show you the reason why, I think you'll understand. I'm really just wanting to expose you, one, to all that stuff that you learned in structural analysis last semester that you forgot, and two, just make sure that you're clear on the usage of some of those design aids. All right, that's homework 2. I do have homework 3 for you. Now, let me be clear. This is an incredibly short assignment. I mean, it's only, oh, you're right, I do. Hold on. This one, that's what happens when you copy and paste. This is wrong. Oh, if I can hit the, oh, go away. There. This is due on the 10th. It's only 2 problems. The only thing with this assignment is to take beams, compute phi-mn, compute the strains, compute the reinforcement limits. That's it. I honestly think you could do this homework right now, and it would take you all of about an hour. Would probably take too much time, so it'll be pretty short. But I do think it's really valuable because homework 4, when we start doing design, I mean, I'm just going to tell you, the design procedures for beams can get a little laborious, so I want the details to be enhanced, which is why I'm doing this assignment. So it's only about an hour's worth of work, but it is an hour incredibly well spent, let me say. Well, you might repeat it during the celebration, so. You might say, yeah, I'm glad we did that assignment. Or you might just say, I don't really want to take an exam. Moment frame, yes. Yes. You can, now let me just really quickly go into that. You can use bracing systems in buildings. It's not to say you can't do that. I mean, people do it all the time. It's just where you put them, you know. Yeah. It's common, for instance, to put bracing systems around the elevators, because who cares about having windows near the elevators? That too, yeah. You can have, in a concrete building, you could do a shear wall, and it'd just be one big solid wall. What's that? No, that's not what I'm talking about. I'm talking about, like, if you are wanting to use a braced frame, like in a building like this, you could put the bracing where the elevators are, because who cares about having windows around an elevator system like that? That's sort of what I'm getting at. Does that make sense? But yeah, by and large, a lot of that stuff is dictated by architectural requirements and things like that. So, sound good? All right. I'm going to mention the SAME Fitzwater Scholarship. The application was actually due yesterday, but the folks at the course said they would do it or accept them today. If you are interested, shoot me an email, and I will forward you the application. You need your SAME member number to apply for that, though. All right, sound good? All right, this homework, again, is pretty short. The next homework will be a little more laborious because we'll be doing full-blown design on that one. Okay. All right, so what we're going to do today is this. We're going to talk about designing economical reinforced concrete beams. This could be a little bit like movie time today because I'm going to talk about some of the derivation. And I warn you, there's going to be alphabet soup. There's going to be, plug and chug and all variables and A sub S's and X's and D's flying around all over the place. But in the end, I'm going to whittle down to a nice, very concise, neat, hey, here it is on design, okay? You don't have the beam charts or the design procedure stuff right now. I'm going to give that to you next time, and then we will go through and work that out. Or did I give you the design procedure stuff? Did I do that? But you have this, right? Okay, all right. So I'm going to take my time with this because I really think this is important. This discussion right now is going to lay the way for how we design reinforced concrete beams. So I'm really going to take my time and make sure it makes sense. All right, so let's get into it. I want to discuss the economics of reinforced concrete beam design, and I want to use the following two parameters, okay? Number one, I want to go back to this, the expression for phi. Remember, that's the linear relationship for phi, right? It's either 0.9, it's either that linear relationship, or it's 0.65. Y'all remember that? Okay. I want to now introduce a new concept to you, and that concept is the idea of a reinforcement ratio, this term rho. And rho is just the ratio, essentially, of how much steel you got to how much concrete you got. Or maybe I should say how much usable concrete you've got, because we're taking B times D, not H, but D, from the top of the beam to where the rebar is. Okay? Make sense? All right. So the area of steel can, instead of being expressed as just how many bars you've got, the area of steel can be expressed as rho BD, the area of concrete times that ratio. See, that's important because we're going to start to enter design mode where we're selecting the amount of rebar, selecting the beam dimensions. So having different ways of expressing this is pretty important. Okay? Does that make sense? Okay. All right. So let's go back to this. All right. So let's take our time with this. So up top on that slide is the method by which we compute A, the depth of that stress block. So let's just go back in time. Let's see if we remember how to do that. So we've got C equals T, right? The force generated by the concrete in compression must equal the force generated by the steel in tension, right? So that's 0.85 FC prime times the area in compression, AB. That must equal the area of steel times Fy. Sound good? We then take that and solve for A. Yes, sir? No. What I'm saying is this. Remember, come on. That is always our stress block, right? The depth of that stress block is always 0.85 FC prime. Remember, the purpose of using 0.85 FC prime is to take that nonlinear funky relationship that goes all the way to FC prime over here on the left and converting that into a simple single rectangular stress block that we can use across the board. Does that make sense? What I'm saying is that 0.85 FC prime over this depth, the compressive force generated by this equals the compressive force generated by this. The advantage of doing this versus that is this requires calculus. I don't like calculus when I can avoid it. Does that make sense? Stay away from the C word? Had your up to your limit with that stuff? Is that what it is? I'm getting you trained up. All right. So where was I? Okay. So what I'm saying here is that the concrete in compression, the force generated by that concrete in compression is 0.85 FC prime AB. Does that make sense? Is that valid for everybody else? This is good stuff. Okay. All right. So that force in compression must equal the force in tension. We solve for A. How deep does that stress block need to be so that C equals T? And we get this, right? Now what I want to do is I want to rewrite that using our reinforcement ratio, rho, okay? So the area of steel, based on what we said before, was rho BD, right? So where I've got an area of steel in right here, plug that in. So instead of area of steel, I've got rho BD. And notice how the B's cancel, right? Because I got a B up top, B down below. There you go. Does that make sense? So that is a way to compute the depth of the stress block, assuming we've got that reinforcement ratio. Sound good? Okay. Now, let's look at moment. How do we get moment? It's force times our moment arm, right? Our moment arm is D minus A over 2, and our force is either ASFY or 0.85 FC prime AB. I'm lazy, so I don't want to multiply 4 things together. I just want to multiply 2 things together. So I'll just do ASFY. Does that make sense? So let's do a little bit of plug and chug. So what do we have? We've got the area of steel, which is rho BD. We already derived that. And then A, well, we just did that on the previous slide. This is rho dFy over 0.85 FC prime. Everybody okay with that? Okay, all right. So if you plug those terms in, instead of AS, put rho BD, and instead of A over 2, well, if this is A, then A over 2, that's where I've got that 1.7. Does everybody see that? Because 0.85 times 2 is 1.7. I can rewrite the moment in a reinforced concrete beam, the moment capacity, as follows. Everybody good? Not too bad so far. Again, I know there's some alphabet soup, but there's a point, I promise. So far, so good. All right. Okay. What I want to do is I want to look at the moment capacity in a reinforced concrete beam, and I want to see what happens if we start changing up some parameters. So specifically what I want to look at is how in the heck does that reinforcement ratio affect things, okay? So what I did is I took this expression, so Mn equals what? BD squared times Fy times all that stuff in the parentheses right here, and I divided this out. Mn over BD squared. So what I'm doing is I just went into Excel, and I said, all right, as the reinforcement ratio gets larger and larger and larger, what happens to this? This is essentially a dimensionless or a dimensionless measure of how strong the beam is, okay? Now, I'm plotting this for 4 KSI concrete and 60 KSI steel. I'm just keeping it basic. I just want to look at the basic parameters. But if you go through an Excel and you plot that out, you're going to get a curve that looks something like this. So what that is saying is as your reinforcement ratio goes up, your beam can withstand larger amounts of load, which on the whole, I mean, doesn't that make sense? You throw more rebar in the beam, it can hold up more load. Simple, right? Here's the problem with that. We haven't talked about our safety factor, phi, right? Do you remember those videos that I showed you of the under-reinforced failure versus the over-reinforced failure? Remember that? Remember the under-reinforced failure? It was almost tough to, did it fail? Like, it didn't look like it failed. It just sort of gave up, you know? But the over-reinforced failure, when you started piling rebar into that beam, when it failed, it went boom. Like, it failed quick, right? The reason why is C equals T. You start piling rebar into a beam, what happens is there's a lot of T, right? So that means the concrete has to generate a lot of compressive force a lot faster. The more rebar you throw in there, the more dramatic the failure is going to be. So we adjust our safety factor accordingly. Under these smaller levels of reinforcement, we're using a phi value of 0.9. But when we start bumping that reinforcement up higher and higher and higher, we get to the point where it doesn't really matter. In other words, we could keep increasing that reinforcement and increasing that reinforcement, but yeah, we're getting a stronger nominal capacity, but we can't use that much of it. I mean, think about it like this. This is a reinforcement ratio right here of about 0.017. So that means about 1.7% of the beam is steel, okay? Now from here to, let's say here, now this is 0.27, right? So from a cross-section that's about 1.7% steel to 2.7% steel. look what happened from here to here. We kept throwing in more and more rebar, but we really didn't get an increase in our usable capacity. Because as we threw in more rebar, the beam said, well, that's great, but now we're demanding more out of the concrete, and we're just not getting an increased level of safety. Yeah, the beam got stronger, but it's not as safe. And that's what fee does. That's what that safety factor does. So throwing in all that rebar didn't really do any good. Make sense? It wasn't really valuable. So maybe there's a point where maybe there's a reinforcement ratio that we can use, a target reinforcement ratio that we can use for design. So let's talk about that. Let's rearrange this expression a little bit. So this is an expression I had a little bit ago that was looking at the moment capacity. That's this, the thing in the box I plotted right there, just moment capacity as a function of the beam dimensions. And if I solve for BD squared, I get that. And that's just rearranging it a little bit and doing all the algebra solving for BD squared. This is a really usable expression in that box. That's really valuable because what that expression is telling you is that based on some material properties, some FC primes and some FYs, and a measure of how much moment you got to resist, you can determine BD squared. And if you can determine BD squared, you can figure out how big your beam needs to be. Okay? The only thing we need is rho. The only thing we need is that reinforcement ratio. If we got that, we're golden. That's all we need. So what I'm going to do is this. Excuse me. I want to talk a little bit about those reinforcement ratios because they really do, they are pretty powerful. Okay? Reinforcement ratios, they can highlight the economy or the economics of your design, and they can be useful tools for design. Okay? We can come up with rho values two different ways. We can come up with rhos based on a given strain value, which can be pretty valuable later if you're trying to meet a certain strain demand. We can also use or come up with a rho value for design purposes. In other words, a pretty straightforward value right off the bat for purposes of design. Now we're currently using the 2014 edition of ACI. ACI publishes a spec every 3 years, so we're probably coming out with ACI 318.17 pretty soon. The thing is, by and large, the grand majority of reinforced concrete design hasn't changed for a long time, and it certainly won't anytime soon. Like 0.85 FC prime, we've been using that since the 40s, and that isn't going to change. Okay? But little things change here and there. One of the things that was in a previous edition of the spec was a reinforcement ratio limit that we used for deflections. And the reinforcement ratio is 0.18 FC prime over FY. It's a really simple calc. Just take, like if it's 4 KSI concrete, 60 KSI steel, 0.18 times 4 over 60, and that's it. We used to use that value to make sure we had enough reinforcement for deflection. But experience over the years has taught us that that is a really good value for starting out a design. I mean, you got to think about it like this. When we're doing a reinforced concrete beam design and we have no clue whatsoever what the beam's going to look like, we have got to start somewhere. Okay? We got to have a few trial values to begin our design. 0.18 FC prime over FY, that is a very useful value for design. Okay? What we can do is use this to come up with a trial shape, some trial dimensions, trial pattern of reinforcement, and then analyze that beam. If we find that the beam is, unequipped to handle those loads, that it's no good, well then at least we got a beam to start with. Maybe we can make it a little deeper. Maybe we can add a couple bars of steel. Maybe we can make it wider, change the material properties, but at least we got something to start with. Okay? This is a very good starting value for design purposes. Sound good? All right. We can also develop a design to generate a certain strain in the steel, which, there are some significant advantages to doing that as well, because as you know, the measure of safety based on, or the measure of safety for a reinforced concrete beam is ultimately measured by how the steel behaves. You know, what is the strain in the steel? If we've got really, really large strains in the steel, hey, that's good. Because if the steel yields a whole lot before the concrete crushes, that is behavior that we want to see any day of the week and twice on Sunday. If we get really, really small strains, that's a real expression. That wasn't even a joke, and everybody's laughing. Goodness. I know. It was my timing. That's what it was, right? Well, they won't be back. There'll be others. So, you'll be ready? I can see. Just don't bring like pom-poms or anything. Wow. Deep. Okay. All right. We'll see what happens, you know. We'll see what happens. Okay, all right. So let's go back to this. So what we're trying to do is develop a reinforcement ratio that reaches a target strain value. So we go back to this, you know, our similar triangles, 0.003 is to C, as some strain at the bottom is to D minus C. So we can develop, you know, sort of rearrange that a little bit and get a C over D ratio equals 0.003 divided by the strain plus 0.003. We can go back to that new definition that we had for A. Remember, that's where we plugged in that reinforcement ratio. We recall that A equals beta 1 times C, so that means that beta 1 C equals that. Divide that over, and then plug and chug accordingly. Everybody okay with what's in the box? Well, if C over D equals that, but it also equals that, set those two equal to one another, solve for rho. So this is another way of generating a reinforcement ratio for design. You can either just use a blanket value, or you can use a value that's trying to achieve a certain strain in the steel. Okay? Is everybody okay with that? I know it's a little bit of alphabet soup, but I think ultimately this should be a pretty followable, you know, process. Everybody good? Okay. So we can use that reinforcement ratio to define ultimately some limits that we can use for design. Okay, this is what you don't have, am I right? Okay, I know you don't have it, and apologies, I will bring this next time. So hopefully we can have a little bit of movie time with this. I'll walk you through this, and then I'll upload this probably by the end of business today, and I'll have printouts on Friday. So we're going to do some procedures for design. I first want to discuss unknown cross-sections, and then we'll have a big example, and then we'll do known cross-sections, and we'll have a big example. Now, the difference between what I mean by an unknown cross-section and a known cross-section is whether or not we're using precast elements. Has anybody ever been to a precaster? Anybody ever seen a precasting place? So you have? No, go ahead. You've seen it. Okay. All right. There are companies that they make a living by precasting concrete elements and selling them to end users. So for instance, in the bridge industry, you might have precast beams. So the beams are precast, and you just truck the completed beam to site and just drop it in, okay? If I go back to, let me go back a little bit. I know I'm going back like crazy, but I want to show a picture. Man, we went through a lot. I'm going way back. Pretty much, right here. Remember this? This was an image of the parking garage off of 3rd Avenue. Those are precast elements. You know, I sort of lied a little bit when I showed you this. I said that this was a beam and this was a beam. This is actually one individual element. The element looks something like this. Like if I cut a cross-section. I'm hurting my chances, aren't I? Well, I wanted it to make sense then and for it to make sense now. I'm wily like that sometimes. Oh, what's that? All right, the precast element actually looks like that. It comes from the precaster in a shape like this. So if you look, there's actually 3 of these, I think, between those bays. So we've got a single element right here, a single element right here, and a single element right here. If you look up, up at the floor, you'll see like right here it's just a solid piece of concrete, but right in here there's a little groove between those 2 ribs where the 2 stack next to each other. Okay? The difference between designing a beam just from scratch and designing one of those is for one of these, you know what the cross-section looks like. I mean, it's a pre-made set of forms. You know how wide this is, how deep this is. You know what the cross-section looks like. And the only thing that you need to do is pick out, how much steel goes here, how much steel goes here, et cetera, and that's it. Okay? So designing for a known cross-section, by and large, is a little easier because the beam, you already know what the beam looks like. It's just pick and rebar. Okay? Unknown cross-sections are a little different because an unknown cross-section, I just say 30 foot, here's the loads, go. So you are starting completely from scratch. You have no idea what's going on at the very beginning. You have to make some initial assumptions right at the beginning and then go to work. Iterate accordingly. Does that make sense? Everybody okay with that? So I wanted you to know what the difference is between, what the difference is between an unknown cross-section and a known cross-section. I've seen them, I've seen them being trucked in, yeah. So, moving on down, go back to where I was. We have gone through a lot. Can't learn that fast. All right, there we go. Okay. Procedures for design. So we're going to handle unknown cross-sections, and then we'll do an example. Then we'll handle known cross-sections and do an example. So there's a good chance I might actually end class a little early today once we get through this. All right, so to start off, let's talk about an unknown cross-section. Okay, so an unknown cross-section is going to be as follows. So this is when we have no freaking clue at all what the beam looks like, what the rebar looks like at all. Okay? And don't worry, I'm going to post all this stuff online, so you're going to have all of this. I'm going to come up with handouts on Friday. So first off, the first thing we're going to do is compute the factored moments. So we are going to know, where does this beam go in a building? We're going to have an idea of the span length. Is it in an office building? Is it in a library? So we're going to be able to get loads. But one load we are not going to have is the beam self-weight. We're not going to have one. So we need to assume it. Okay? Right there's an assumption right off the bat. We have to assume the beam self-weight. Now, if you have no clue what the beam looks like, you can use some starting values to sort of get yourself going. In order to compute the self-weight of the beam, you're going to need 3 things. You're going to need the unit weight of concrete, you're going to need the width of the beam, and you're going to need the height of the beam. Now, the height of the beam is pretty simple. You can go off of an ACI requirement for deflections that says, based on whether or not it's a floor beam or it's simply supported or it's a slab or what have you, you can get heights pretty easily. So a simply supported floor beam has to have a height of at least L over 16, okay? So you can take the length, divide it by 16, and get a height, okay? Then you might say, okay, just for rough estimate, here's the height. Let's say the width is about half that. So there's the dimensions of the beam. As for the unit weight of concrete, just take it to be 150 pounds per cubic foot. And then now you can compute a self-weight. It probably won't match your final design, but that's where iteration comes into play. You're going to have to go and update that later. Sound good? All right. Another assumption. Once we get our factored moments, mu, we're then going to divide that by phi to get a required nominal moment. Because remember, phi mn has to be greater than or equal to mu, so this will tell us how much required mn. Now, we're assuming that phi is 0.9, which is what we would like. I mean, we want tension-controlled sections. We might not get that, but we want that to be the case. All right. All right. So once we get mn, next thing we've got to get is a rho value. My sort of policy or philosophy is that unless I'm told otherwise, I'm going to use 0.18 FC prime over Fy. If you've got a problem in the book that says design for a strain in the steel of 0.005, then you're going to go and use that and just plug in a strain value of 0.005 and solve. It's a little more difficult, but the design will hinge closely or sort of zero in better on that target strain value. Okay. Sound good? So once we got a required MN and we've got a row that we can use for design purposes, we can compute the required BD squared, how big the beam needs to be. And so basically we're computing kind of a section modulus. So once we get that, we just choose B and D values such that BD squared is bigger than that, and then we go to work. My advice is do not design a beam that is 15.364827.396 inches wide. Just go with 16. Just keep it simple, 1-inch increments. We're choosing B and D values, but the height of the beam is probably going to be a little bit larger than that for cover requirements. So we'll go with a height, usually, unless you're told otherwise, a height that's 3 inches larger than the depth. So it might be a 12 by, let's say, 30-inch beam, but the steel, from the top to the steel, is only 27 inches. Does that make sense? Okay. Once we've got the dimensions, we can use that row value and say, well, row BD will give us the area. Take that area and choose a reinforcement pattern that is as close to the area of steel as possible. Now you've got a beam. Analyze it, If the beam works, yay. If not, iterate. Maybe add some steel, change the depth. And we'll talk about what parameters will affect the design more than others, okay? Some of them will matter. I mean, you'd be surprised how little FC prime really matters. Like if I go from FC prime of 4 KSI to 8 KSI, you'd be surprised how little that actually affects the capacity. But taking the depth and increasing it by 2 inches, you'd be surprised, So we'll get into those discussions as we go. A couple other things I do want to point out. So we have to consider cover requirements. Have you all heard of cover? I think I've mentioned it, but have you heard of cover in other classes? Materials, okay. So cover is essentially how much concrete stands between a piece of rebar and the environment, okay? Now, different requirements for cover are going to be applicable for different regions. For instance, cover for, let's say, the second floor slab in this building is going to be different than, let's say, a bridge beam out in Miami. Because if it's a bridge beam out in Miami over the water, it's going to be exposed to that corrosive environment of the salt water, right? So we might have like an inch or two cover requirements for a floor slab here in this building, but we might have 6 inches of cover requirement or 4 inches of cover requirement out there because the conditions are worse. I mean, think about like this, cover requirements for bridge slabs in the U.S. or around this region. So here we've got a slab. There's usually 2 layers of reinforcement, the layer on the bottom and the layer on the top. Now the layer on the bottom only has a cover requirement of 1 inch, but on the top, 2.5 inches. Why would we require more cover for the top layer than the bottom layer? What is the top of a bridge deck going to be exposed to in West Virginia that the bottom isn't going to be exposed to? The icing salts, right? But there's actually something else that goes along with that. What else is going to run along the bridge throughout the winter? What did you say? It looked like you said something else. Yeah. What else? Somebody said the plow. What do you think that plow is doing to the deck? It's scraping the deck. You're going to get a little bit of material removed off each time. I mean, when we do bridge design, we actually account for, in our calculations, we say, well, the total thickness of the deck is like 8.5 inches. But we assume half that, or like half an inch, is just gone for resistance. So in other words, when we compute the weight of the slab, we take 8.5 inches. But when we compute how strong that slab is, we only take 8 inches because we assume half that isn't really going to help us at all. Yes, sir. I'd say yes, but I doubt that many structural engineers are really thinking about that, and here's why. Because when you cast concrete, let's say for a bridge deck, or for a slab in a building, or a column in a building, or a beam in a building, by and large, there are ASTM specs that you're going off of just to ensure that you've got the right mix design, that you've got the appropriate admixtures, and et cetera. So you're really not, that doesn't really become a big issue. From a structural engineer standpoint, what we're more interested in is detailing the cross-section accordingly so we got enough distance between what's going on inside the element and the environment. So again, going back to my bridge slab analogy. Now let me say this. I mean, you know, if you've got a deck that's got some cracks and you've got chloride penetration going on inside that deck, you can get a massive amount of corrosion inside the deck. That's bad, because what does metal do when it rusts? Breaks. But what is it from a volume standpoint? It expands. And think about what happens if you've got corroding rebar inside a reinforced concrete element and it's expanding. That is bad news, right? Bad news. So, I mean, there's actually a whole science in reinforced concrete design called ECE. It stands for electrochemical chloride extraction. And without getting too technical, you basically have a cathode and an anode, and you stick a car battery onto it. It's a little more technical than that, but you're essentially trying to draw out that chloride penetration out of the rebar to prevent the propagation of all that corrosion. So it's a pretty nifty, you know, little exercise. So yeah, does that make sense? A little bit of a tangent, but we've got time to do that, so I really wanted to address that. Does that help answer your question? All right. Everybody else, this is good stuff. Now, I'm going to pull up a design aid that I'm going to give you here in a little bit, but I really want to explain a little bit in more detail about the anatomy of a typical reinforced concrete element. Has anybody ever seen, you know, like a casting going in place and seen all the rebar getting tied in? Anybody ever seen that? It's usually pretty complicated. For instance, in a reinforced concrete beam, I mean, like let's say here's the beam. So the beam's going to go from here to here, and here's the formwork. There's a lot going on. First off, you've got that bottom layer of reinforcement. That's the actual tensile reinforcement here that's resisting the loads. But then you also have these sort of, you know, U-shaped things going on. You ever seen those? Those are called stirrups, okay? And they're there for two reasons. One, to keep all the rebar in place, but two, we're going to spend a lot of time detailing those stirrups later, because those stirrups are how the concrete beam resists shear. They are the reinforcement for shear. But then the third, if you've got rebar at the bottom and you've got these stirrups going all over the place, you usually put a couple hangers up top to sort of tie everything together, and you get what's called a rebar cage, and you just sort of sit that down, sit it on some chairs, and then start casting your concrete in. Sound good? So the spacing of that reinforcement inside the beam makes sense. So to give you kind of an idea on cover, so okay, first off, from the edge of the beam to the stirrup, for beams that are not subjected to de-icing salts or exposed to weather, which is really going to be the case for most beams inside a typical reinforced concrete structure, the cover requirement is about, or is 1.5 inches. Okay, that's for beams inside, not subjected to de-icing salts. So if you think about it like this. Okay, so let's say I got number 10 bars. Let's just think about the dimensions. Okay, so placing these number 10 bars in the beam, I got to come in 1.5 inches, come in 1.5 inches. Then I got to come in however wide the stirrup is. So if this is a number 3 stirrup, I got to come in 3/8 of an inch on each side. Everybody okay with that? Then if I got number 10 bars, I got to provide an appropriate amount of space in between those bars. Make sense? So bar spacing is the minimum of either 1 inch or however wide the bars are. Okay? Make sense? So let me show you something real quick. And this is something I'm going to give you on Friday, and I'll post this as well. This is a little beam design aid that I came up with that'll make your lives a little easier during design. First off, this first table you all should be able to produce in Microsoft Excel in about 5 minutes, okay? Because all this is a table that lists, if I've got, let's say, number 9s, and I've got 4 of them, the area is 4 square inches. Simple, right? If I've got number 7s, and I have 8 of them, so 8 number 7s is 4.81 square inches. So this is just gives us a nice little multiple table of the area of bars, okay? Sound good? Now that's the first aid, but the one that's down here I think is the one that's really worth its weight in gold, and that's this right here. So it is the minimum, essentially the minimum beam width or the web width for beams with inside exposure. So what this will tell us is this. So let me go back to my little image right here. So I have here a beam, let's see, I've got, 3 number 10 bars? So let's be clear, I got to have cover on each end, I got to have, let's see, a stirrup on each end, I got 3 bars, and then I got to have space in between. What this table tells me is if I have, let's say 3 number 10s, if I have 3 number 10 bars, I have to have a beam width that is at least 10.4 inches wide, okay? So that's accounting for 1.5 inches of cover on each side, the stirrup, and then the spacing in between, not to mention the width of the 3 bars. Does that make sense? So keep in mind, this table was built based on number 3 stirrups. If you had like number 4 stirrups, you could develop a new table. By and large, number 3 is going to be mostly what we use. In steer, and when we look at shear, we rarely ever use either number 3s or number 4s, and number 3s are typically what we use predominantly. So when we go through design, let's say we do all the math, and the math says we need 6.7 square inches of steel. So what we'll do is we'll say, all right, let's go up here and let's find some iterations that meet that. So 6.7 square inches of steel, I could get by using 5 number 11s. Everybody see that right there? 7.81. I could use 6 number 10s, and so on and so forth, right? So what I might do is I might say, okay, let's see 5 number 11s. Is that a viable option? So I go down here, and I say, well, if I got number 11s and I have 5 of them, my beam has to be at least, 16.6 inches wide? And if my beam's only 14 inches wide, then I got to pick another iteration because, yeah, it's a nice amount of steel, but I don't have the room to fit it into the beam. Does that make sense? So we'll go through, that's how we'll go about this once we start getting into design. We'll pick sort of representative families of reinforcement. How many number 7s, how many number 8s, how many number 9s. And then for each of those, let's see, is it a viable option? Can we actually fit that many bars inside the beam? If the answer is yes, let's just catalog that for all of them and pick the one with the smallest amount of steel and go with it. If not, eliminate that option and move on. That make sense? All right, anybody got any questions? Yes, sir.
So is the cover the same value as H minus D?
No. Okay, so that's a good question. So when we do our design calcs, we go with H minus D of 3 inches. Okay, I'll say this. So H minus D of 3 inches, or that equals 3 inches, is a very common value for design for a few reasons. One, it meets the 1.5 inch cover requirements that you're mentioning. That's point 1. Point 2, have you ever heard of a rebar chair? Have you ever heard of a rebar chair? Has anybody else ever heard of a rebar chair? Okay. A rebar chair is a little piece of plastic that you can buy from a place like Lowe's or a Precaster, and it's a little stand. It looks, here, I might even pull an image of one up, because this is important stuff. So it can be made of plastic. Sometimes it can actually be made of metal, and it's, maybe galvanized or something like that. Come on. goodness. Okay, here we go. This is what a rebar chair looks like. So,
It's a literal rebar chair.
that's pretty good. Here's a good one. So this is what a sort of a rebar chair looks like. It's just a stand for the reinforcement to go into. So those come at pretty even increments of height, 2 inches, 3 inches, etc. So that's a pretty common height for a rebar chair. Does that make sense? That's the thing. If you've got your forms, you're going to set your rebar down. It's being set up and down. It's got to sit up a little bit. So you're going to sit it on a chair. So that's a pretty common height. It meets your cover requirements and the like. What? Well, no, okay, that's a good point, but we're talking about beams that aren't going to be on the ground. They're going to be up here. You know what I mean? So you have to have the chair inside the forms. So you have to have something that'll sit in the form, something like that, or not like that. But see what I mean? Like that's going to go inside like a slab. Like not a slab on grade, a slab on the 6th story of a building. Does that make sense? That's a good question. So that's a good point. And yeah, but the rebar isn't. That's a good point. Yeah, because isn't there it's exposed to the surface? Yeah, but it's that the rebar isn't. We're not worried about, I mean, these are usually made out of like plastic. We're not worried about the plastic really being exposed to de-icing salts and behaving, the way we wouldn't want it to. It's the rebar that we're worried about. This is good stuff.
If it's exposed to the surface, could it allow anything to sort of seep through?
You're talking about the chairs?
Yeah.
By and large, I'm going to say the answer to that is no. That's usually not a big concern. I mean, it can be a concern. I mean, I wouldn't, but I think it also just depends on maintenance and your detailing. I mean, if it's inside of a building, if it's insulated and built properly, you shouldn't be getting large collections of moisture. So, sound good? We're going to be doing some full-blown design next time. I'm going to show you all how to design a reinforced concrete beam from start to finish. We're going to look at a 22-foot long beam, dead load, live load, got some parameters, pretty basic stuff. We're going to go to town. Sound good? Sign-in sheets around if you haven't already signed it. Don't forget your homework. That's all I got.
When does your next person come in?
It's here and there.